Sharing screen. I may have to start taking attendance and taking off points for people who don't show up. I hate to do that because, you know, I want people to manage their time and choose when they come to class and when they decide to watch the video. But all my classes, attendance is just plummeting, and it's not the same watching the video, and we're at the goods now, right? This is the essence of 215, which is leading you into recursion, which is the essence of 222, which is basically the essence of data structures, which is computer science. So it's like, this is like the future, you know. I don't have to preach to the choir because you're here, and, you know. But anyway, we'll see. All right, so let's see. First things first. So any questions with eyes towards the midterm on Friday? And it may be a snowy midterm, but I'm not planning on postponing it if it snows, because presumably everybody is able to get to their computer. Yeah, main advice would be go over the homeworks, go over some of the homework questions that I didn't assign, but that are from the relevant sections of the text. Because, you know, the homework questions that I assigned, we talked about them in class. We talked about them after I graded the homework. We've gone through them one-on-one sometimes. So look at some other questions in the same section of the text, and just sort of make sure you're not just remembering, you know, one particular proof, for example. But yeah, if you can do the homeworks, if you do a quick review of your notes, you should be fine. It includes modular arithmetic. It does not include the induction stuff that we started doing today, or Monday. But it includes, you know, congruence and divisibility and, you know, A divides B and that kind of stuff. All right, so I graded and gave back your homework, and for the most part, the homework looked really good. So if you didn't get any comments, then I've got no worries about how you did. I basically looked at the proof questions, so 2 through 5, and I started with question 2, and I looked at that, and if what you did seemed, you know, totally squeaky clean, solid, had everything like right where it should be, I said good to go, and you got 20 out of 20. If I saw things on there that concerned me, then I went on and I looked at question 3 and question 4 and question 5, and if you know, most of that looked spot on, and there were a few issues in 1 or 2 of the questions, you'd still get 20 out of 20. And in some cases, I could see from, you know, the collection of work that you had done that you really had the right idea, but there were issues with each individual solution, and you may still have gotten 20 out of 20. So here's the important thing. Even if you got 20 out of 20, make sure you look at my comments, okay? So that's really important for the exam. Because on the exam, I'm going to grade every single question. I'm not going to say, oh, you got, you know, these questions right, and you missed a few on these other ones, but I'll give you 100 because you seem to have the right idea. Can't do that on the exam. So make sure you read the comments and ask questions about that. Let's see, so if I asked why is n times n equal to 2n, why would n times n be equal to 2n? I mean, unless n happens to be equal to, you know, 2 or 0, n times n is not equal to 2n. But if you meant n times n is even, then you could say, you know, n times n is equal to 2 times k, where k is an integer. That would totally work. But be really clear with these variables that we start tossing into our proofs when we talk about evens and odds and stuff. Be really clear that you're using those variables correctly. And if we're doing a proof about the number n, we can't use n as an arbitrary integer. Does that make sense? So issues that I saw, and unfortunately where I saw most of these issues were from people who are not in class right now, but hopefully they're going to catch this later. But where I saw main issues and where I took off lots of points, not a proposition, okay? Every single thing that you write in your proof has to be a proposition with a number to the left and a reason to the right, right? And most people who are here know this, and we've been doing this, you know, every time we write proofs, it's like, you know, 1, x is even, hypothesis. 2, x equals 2k, where k is an integer, definition of even, right? Always start your proof with what you're trying to prove, right? Prove the sum of 2 even numbers is better than a chicken, right? And then you start writing down a series of steps. Since everything you write is a proposition, it has a truth value. And to be a valid proof, every proposition you write has to be true. And it's true either because, you know, we know it's always true, like 1 plus 1 equals 2, or because it follows from previous things that you've written, possibly applied with, you know, combined with laws of logic, or the real starting point for all of this because it's a hypothesis, because it's something we're given. Prove if x, then y. Okay, step 1, x. That's the hypothesis. Step 2, the moon is made of green cheese. Step 3, cheese is better than mayonnaise. Step 4, y. Right? Now you started with x and you managed to prove y. You're done. QED. Okay, so not writing propositions, that was a problem. Not doing a proof, that's a big problem. So if you argue, you know, well, if a number is even and you multiply it by itself, since your number was divisible by 2, the product is still divisible by 2, and so that's an even number. That's a really great line of thought, and that's really good for figuring out how you're going to put together a formal proof, right? But that's not a formal proof. All right. Similarly, if you miss the reasons, if you don't list reasons, but you just list all the steps, right, that costs you points. Again, on the homework, I might have only taken off a few points for that because, you know, I could tell from the steps you wrote that you probably had good reasons for those. But on the exam, right, that would cost you a lot of points because that would not be considered a valid proof. All right. So those were the main things, and like I say, I think everybody who's here, you know, has seen this done in class, and you've done this on homework, and so I don't think that's a problem. But just be really clear that you know, the presentation matters. The style of showing whatever it is you're trying to show is a big part of the point of doing these proofs. Let me talk about the next homework assignment. And this one's going to be kind of weird because, you know, Friday's an exam, Monday's a holiday. So we won't really have a lecture opportunity until a week from today. And I don't like giving homework and asking you to turn it in before we've had a chance to go over it in class. So, so your next homework is not due until a week from Friday, which is really dangerous because there's a chance that you won't even look at it until, you know, next Thursday. I'd like you to look at this soon, okay, and be thinking about it. So these are induction questions. And come to office hours if you're not sure how to do these. and work on them, right? They're proof problems, so they take fiddling around with, but we've gone through the basic process of induction. We're going to spend the whole class today doing inductive proofs and thinking about what they mean. So after today, you should be in pretty good shape to do these problems. And I'd like you to start working on those sooner rather than later, right? And you can come to office hours Thursday, Friday, Tuesday, Wednesday, and you can ask about these in class Wednesday, right? So don't just kind of push it out of your brain. So these come from the additional CSE215 text. So on Canvas, there's a link to the additional text. This is going to be really painful to go through in here, I think. So let me see if I can. Yeah, it's not going to bring us any joy, so I'm just going to go directly to it. All right, and this is all good stuff for proof examples and so on and so forth. So 3.4 in mathematical induction, and you'll have seen some of these examples in class. So exercises. So I asked you to do questions 1, 5, and 6. And these will get all twisty turny with algebraic manipulation. And I won't ask you to go really heavy during an exam with algebra, but work through it, right? It's a good refresher of algebra, but you know we're mainly after the induction part. So you know this is one that we already that we'll look at today. We'll play around with these, and then write up 1, 5, and 6 for submission, and in the next section 3.5. Look at questions 1, 8, and 9. So more induction here. This is a fun one. And then these two are pretty harmless. No induction proofs on the midterm. No induction at all on the midterm. All right, let's see. I know we've already moved on. We haven't. But really just quick on problem 3 for the previous homework. I had a step where I said n times n plus n equals 2 times 2k squared plus 2k. And the next step was 2 times 2k squared plus k. So yeah, 2 times 2k squared plus k is not a proposition. But if you had written n squared plus n equals 2 times 2k squared plus k, yes, that is a proposition. So that's exactly what I was after there. Good deal. All right, let's start working through some proofs, and we'll start again with a very mathematical proof that we'll do with induction, and then I want to go to a very different feeling example of something we can prove with induction, and this will take us somewhere really interesting. But let's start with with an algebraic one. Let's see, when I do algebra and proofs, I show every step. It makes them a bit longer. Do I need to do that, or can I combine? You can combine a few steps as long as you don't skip over anything that's not obvious. For example, you know, if you have n squared plus n equals 2k squared plus 2k equals, and if you want to just go ahead and write down what that is without making errors, that's fine. So, I mean, certainly I would do 4k squared plus 2k equals 2 times 2k squared plus k. I think I made an error, right? That's fine. But I wouldn't just go directly from here to here, right? Show me the substitution, and then if you want to do all kinds of magic to turn this into something that's pretty obvious, right, go ahead and do that. But if you have to do fancy things like, you know, square root it, multiply by the square root of the sun, and multiply it by 17 and divide it, you know, so as long as it's an obvious step, feel free to skip it. If you want to combine, you know, 2 times k into 2k squared, you don't have to show that. Yeah, you can use the square root of the sun, totally. That's when you're really stuck on a proof. Just throw that in. And if the teacher is lazy, they'll be like, I don't want to calculate the square root of the sun, I'll just give you credit. Alright, so let's do some of the odd integers. So I'd like to show what we get when we add up odd integers. So I'm going to add the first n odd numbers together. So if I is 1, this will be 1. If I is 2, this will be 3. If I is 3, this will be 5. And I'd like to prove that this is always equal to n squared. And I'm going to go ahead right off the top and put my ignore section over here. Alright, is this true? Well, let me try some examples. N equals 1. Sum from I equals 1 to 1 of 2i minus 1 is just 2 times 1 minus 1, which is just 1. Well, that is 1 squared. What about n equals 2? Sum from I equals 1 to 2 of 2i minus 1. Well, if I is 1, that's 2 minus 1 is 1. If I is 2, that's 2 times 2 is 4 minus 1 is 3. That's 4. Hey, that's equal to n squared. So this seems plausible. Alright, this is what I'm trying to prove. I'm writing it down at the top of my proof so it's clear what the goal is here. We need to do a family of propositions anytime we're going to do mathematical induction. So let's make a collection of propositions, and we want to prove this is true for all n bigger than or equal to 1. That's how we know we want a collection of propositions. So I'm going to say let P of n be the proposition sum from I equals 1 to n of 2i minus 1 equals n squared. So what we really want to prove is P of n for all n bigger than or equal to 1. And I gotta have all of this stuff before I start writing all these statements about P of n. I gotta know what P of n is. Right? You know what it is. Make sure the person reading the proof knows what it is. Okay, we're going to do this with mathematical induction, so we have two steps. 1, prove P of 1. Show that the proposition is true for n equals 1. Well, you know, P of 1 says what we just did on that other piece of paper, sum from I equals 1 to 1 of 2i minus 1 equals 1 squared. Well, this is 1 and this is 1 and those are equal. So yeah, P of 1 is clear. That doesn't take a whole lot of work usually. Okay, second step. Prove that if P of n is true, P of n plus 1 is true. As long as n is bigger than 1. Bigger than or equal to. Okay, this is the main object of our proof now. We've got a base case. If we can prove this, then we can tie it all together in a bundle, write mathematical induction on top, and there's our proof. So our whole focus now is just proving P of n implies P of n plus 1. Okay, so now we're going to do what we've been doing and write the steps of a proof. So what's our first statement? Perfect. P of n. Why do we know P of n is true? That's the hypothesis. Nice. What's our second statement? Definition. Perfect. Let's write down what P of n says. P of n is the proposition that this is equal to that. We've just said P of n is true, which means this is true. So let's put that in our proof, because that's a lot of stuff in there. Maybe we can use something. Sum from I equals 1 to n of 2i minus 1 equals n squared. That's the definition of P of n. Now it's the Wild West. We could go a number of directions here. We got to figure out what's going to be useful. So what are your thoughts? What could we try to do at this point? Because honestly, we don't have a lot to work with yet. Solve for I plus 1. Okay, so doing a plus 1 somewhere is going to help us. So step 1. Oh, so this step 1 is pretty much unrelated to this step 2. Right? Step 1 we just do once, and then we kind of put it aside. And then we do step 2 and we put that aside. And then we take those two results, we put them together and say mathematical induction. Bingo, we're done. So yeah, we're not going to come back to this until we've finished step 2. But what would we like to prove? We'd like to prove P of n plus 1, right? That's our goal here. We assumed the hypothesis, we wrote down the definition, we're going to square root the sun or whatever, and hopefully we're going to end up with P of n plus 1. So let's look at what P of n plus 1 says. Let's look at it in the ignore area, right? So P of n plus 1 is the following proposition. Sum from I equals 1 to n plus 1 of 2i minus 1 equals n plus 1 squared. All right. All we know is this. What we want to show is that. And most of these questions that have these sums in them, we're going to use the same kind of trick, which is if I were to take this sum and just add one more term to it, it would end up being this. So I can make this left side look a lot like this left side by just adding one thing to it. And without necessarily knowing if that's going to help us or not, let's just go ahead and do that. So I'm going to write down the following indisputable fact. Sum from I equals 1 to n plus 1 of 2i minus 1. And I'm going to split it into two smaller summations. It's the sum from 1 to n of 2i minus 1 plus one extra term, which is when I equals n plus 1. So yeah, effectively that's right, sum of P1 plus sum of Pn, but be really careful about that. That's really good intuition, but definitely don't write something like that as part of your proof, because Pn is not an expression of the mathematical type. Pn is a proposition, so we can't really do like sum of P1, but we can take the sum that we saw, you know, in Pn and do something with that. Yes, we're still doing mathematical induction. And in particular, we're trying to prove that the sum of the first n odd numbers is equal to n squared. Alright, anybody have trouble with why this is a true statement? It really has nothing to do with anything that came before. Oh, those Windows updates are brutal, man. Right? This is a statement I could write any time that I want. This is always true. The sum of the first n plus 1 odd numbers is the sum of the first n odd numbers plus the n plus first odd number. So everybody okay with having this as part of our proof? I never realized just kidding was the same abbreviation as like JK flip-flop. Maybe that's why 250 is the way it is. Alright, so far so good. Alright, what's nice about writing this sum like this is that I have a way to replace this piece of my expression that uses this step up here. So I can certainly say this is equal to, well, the sum from 1 to n of 2i minus 1, that's n squared. And so if this is n squared, and then I just leave all of this exactly as it is, that's algebra and substitution of what we wrote in 2, where we replace this summation with this n squared. Well, now I'm just going to go to Algebra Town. N squared plus, and this is 2n plus 2 minus 1, which is n squared plus 2n plus 1, and that's more algebra. And n squared plus 2n plus 1, that's n plus 1 squared. And that's still more algebra. This n squared came from the fact that this summation is equal to n squared. How do we know that? We said that was true in step 2. All right, that's the magic part. You do a little bit of magic and then you throw in a bunch of algebra, and what have we got now? The sum up to n plus 1 is equal to n plus 1 squared. Well, what is another name for the proposition that the sum from 1 to n plus 1 is equal to n plus 1 squared? That's just p of n plus 1. So now we can write down p of n plus 1. That's the definition of p. And so what have we done? We started with Pn, we proved P of n plus 1. Therefore, if P of n is true, P of n plus 1 is true. Now, we put together the fact that we proved a base case, P of 1, and we proved an inductive step for all n bigger than or equal to 1. Put those together, and that proves P of n for all n bigger than or equal to 1 by reason of mathematical induction. That's what you were asked to demonstrate. Alright, again, there's a bunch of moving parts here. There's the algebraic magic, which I'm not too worried about, even though you need that to be able to complete the proofs. There's this business of, splitting the sum into two pieces, replacing that with n squared, factoring, all of that kind of stuff. That may be, the trickiest part of the proof, and that may be where the insight comes in. I'm not too worried about that for today, okay? There's the mechanics of, doing a formal proof, stating reasons, and so on. That's very important. And then there's the part that's fundamentally new, which is we can take a base case and an inductive step, combine them, and come up with this really powerful statement that this proposition is true for all n. Right? That's the mathematical induction piece. So questions about that? Okay. So I'm going to go on to another example, and we're going to start getting into the reason why we care about mathematical induction. This is the course. This is the whole game. Go over it again. What part do you want to go over again? Well, let me move on to another example. It will be the same steps, right? Different specifics. But like I say, it's the steps that I want you to catch here. But if you think you missed something in particular, you can go ahead and ask, and we can go over that. All right, this is the ball game right here. Okay? We're going to do a few more examples like this, and this is really the essence of why you're taking CSE215, okay, and why this works with CSE222, and this is what we're going to be doing in 222 for the rest of the quarter. So let's look at a very peculiar example. Suppose you have a kitchen floor, and it's covered with tiles. This is the actual size of my kitchen floor, by the way. It's arguably the smallest kitchen I've ever seen. Not that I'm complaining, because I love my kitchen. But I mean, you have to close the cabinets if you want to, like, turn around. All right, so you have a tile floor, and you know it's covered with these little tiny decorative tiles, and after a while, you know, these tiles start to break and they're missing and all this kind of stuff, and you decide I'm going to re-tile the floor. Okay, so you go to, you know, your favorite store and you price out tiles, and tiles are really expensive. You know, because you don't want just any tiles. You want like really, you know, fancy tiles. And they're really expensive. You can't afford to get, you know, all of those little individual squares. So you leave the store and you're kind of dejected and you're not sure what you're going to do. And somebody's like, hey, come over here. I hear you're looking for tile. You're like, yeah. You're like, come over here. Let me show you something. They pop the trunk and they've got a whole box of tiles. And they're like, let you have the whole box for $5. No. Yeah, he's wearing a trench coat. And you're kind of suspicious, you know, like, let me look at these tiles, and you look at them, and instead of these tiles being squares, they're all L-shaped. They look like that. Now the price is right. You can get like a whole box of these, more than enough to cover your entire huge kitchen floor. But, you know, they're shaped like these little L's. And that's a little weird, you know. So you start wondering, could I cover my floor with these L-shaped tiles? Now, I know, you know, I could take this L-shaped piece, and I could take this L-shaped piece, and I could cover a little 2x3 region. Yeah, it's Tetris, right? Now, it turns out, and I didn't draw this to scale, but it turns out that your kitchen floor is 8x8. So it's 64 tiles. Now, common sense tells you, you know, each of these little L-shaped things is 3 tiles. So if I use a bunch of them, right, my whole floor is going to be, you know, some multiple of 3 squares that I cover. Well, 8x8 is 64, right? So I'm not going to be able to cover every single tile using these. But it turns out there's one spot you don't want to tile. There's this tile right here. You've got a pipe coming up through the ground right there. And you don't want to cover that. So I've only got 63 tiles to cover, and I've got, you know, a whole box of 3-sided tiles. Could I cover my floor with these L-shaped tiles? So there's basic rules. You're not allowed to cut the tiles. You're not allowed to overlap the tiles. You're not allowed to go outside of this region. And you want to cover every spot except this one tile. And the question is, can you tile the floor? And the answer turns out to be yes, you can. And it turns out, as long as your floor has dimensions 2 to the n by 2 to the n, you can tile your floor. And we will now show that with mathematical induction. Good idea. Alright, so other than the 2 to the n part, there's really no math in sight here. But that's okay. So let's let P of n be the proposition. You can tile a 2 to the n by 2 to the n floor with one missing square using L-shaped pieces. Alright, so P of n is the proposition that you can tile a 2 to the n by 2 to the n floor with these L-shaped pieces, following all the rules about not cutting, not overlapping, and so on, and covering everything except for one missing square. And we would like to show that P of n is true for all n bigger than or equal to 1. And we're going to do this with mathematical induction. And then we're going to see something really cool at the end. So what's our first step of a mathematical induction proof? Even though this isn't very mathematical, it'll mimic mostly what we've been doing. So yeah, first step, prove P of 1. We need a base case. So P of 1 says you can tile a 2x2 floor. I'm not going to write the whole thing out, you know, with one missing square, with no overlap, etc., etc. So P of 1 says you can do this for a 2x2 floor. Well, we can demonstrate P of 1 very easily. So let's make a 2x2 floor. I'll make a few of them. And we are going to have one square missing. Well, since there's only 4 squares, there's only 4 possibilities. This square could be missing, or this one, or this one, or this one. Well, I can demonstrate a way to tile each of these. If this is what my floor looks like, I'll do an L-shaped piece like that. If this is what my floor looks like, I'll do that, and so on. Bingo, P of 1 is proven. Everybody agree with that? So P of 1 is true. We're halfway there. That's our base step. Now we have to do the inductive step. Inductive step. Prove that P of n gets us P of n plus 1. Is that really a valid proof? Well, you know, yeah, for floor tiling 101, that's totally valid. You could make this very mathematical by you know, coming up with some way to describe the arrangement of tiles and where the position of the hole is and so on. But you know, since we are doing a particularly mathematical proof, I'm going to get away with hand waving, and I won't ask you to do this on an exam. And again, this is illustration of the concept. But you're right, it's not very rigorous. This is going to get less rigorous, all right, but indisputable. So let's prove P of n gets us to P of n plus 1. Okay, so here's what I'm going to do. I'm going to draw a picture of your floor. This is going to be 2 to the n plus 1 by 2 to the n plus 1. And step 1, you know, we're going to assume P of n is true. That's our hypothesis. We want to show P of n plus 1, which means we want to show that this can be covered with 3-sided tiles minus 1 square. Alright, I'm going to split this room into 4 smaller rooms. So how big is each of these small rooms? P of n plus 1 over 2, which is also, well, not P of n, 2 to the n plus 1 over 2. which is 2 to the n. No, this is not on the midterm, but it will be on the final. Alright, so each of these little rooms is 2 to the n by 2 to the n. Okay, just like the base case, I'm going to break this proof into 4 separate possibilities. We're going to have one tile missing from this room. Now, it could be missing from this quadrant, this quadrant, this quadrant, or this quadrant. It's not going to make any difference to us. Okay, so I'm just going to assume that there's a tile missing from somewhere up here. But technically, I need to do 4 versions of this proof. One where it's missing from here, one where it's here, and so on. But the proof won't change. It would just be kind of repeating the same process. So in mathematics, we sometimes say, without loss of generality. And then we say, you know, let the missing tile be in this first quadrant. But it just means I don't want to write the whole thing 4 times. Okay, so suppose we're missing this tile. Can we cover the rest of this 2 to the n plus 1 by 2 to the n plus 1 room with all shaped tiles? Yes, we can, and it's really easy to do. Okay, so what do? First, cover this quadrant. Fill in this whole upper left quadrant with L-shaped tiles, everywhere except that spot. Can we do that? Can we fill in this upper left quadrant with L-shaped tiles? Let me rephrase it. We can cover this upper left quadrant with L-shaped tiles, but why? How do we know that? It's a 4-character answer. How do we know we can tile this upper left quadrant? Because it's P of n. P of n is true, and P of n says we can cover a 2 to the n by 2 to the n square missing one tile. Well, that's what this upper left quadrant is. It's 2 to the n by 2 to the n, and it's missing a tile. So because we know P of n is true, we can cover this floor perfectly with that one spot missing. Everybody see that? So we've got a quarter of our task done. We've got a quarter of the floor covered perfectly. Now we have 3 more quadrants to do, but they're not missing a tile. So we can't say, you know, because of P of n, we can cover this perfectly and this and this. P of n only says we could cover this region if we were missing a tile. So let's remove a tile from here for now. Let me just remove this tile in the upper right corner. Well, what am I left with? A 2 to the n by 2 to the n region with one missing tile. P of n says I can cover this perfectly. And let me ignore this tile over here. And this is a 2 to the n by 2 to the n region with one missing tile, and P of n says I can cover that perfectly. So I'm making some progress. I'm going to ignore this tile up here. And this is a 2 to the n by 2 to the n region with a missing tile. And P of n says I can cover that region perfectly. So I've used a bunch of L-shaped tiles, and I've covered my entire floor except for, you know, this one square that I don't want covered, and this one little L-shaped piece in the corner. And now I take one more L-shaped tile and I pop that in right here, and my whole floor is covered. Yeah, you had the insight. Therefore, P of n plus 1, so P of n implies P of n plus 1, therefore P of n for all n bigger than or equal to 1, and we're done. Okay, so I'll grant you that's a little weird. But if you follow each of the steps, you're forced to conclude that, you know, this is a proof that we can cover any 2 to the n by 2 to the n floor with L-shaped tiles. This was the P of 1 case. So P of 1 says a 2 by 2 room with one missing tile can be covered. All right, so that's a proof, and that's a valid proof. We'd need to put, you know, more formalism on it to turn it into something mathematical, but logically, that's a completely valid proof that you can always cover a 2 to the n by 2 to the n floor. Okay, so here's the magic part, right? We've proven that you can tile a floor in this way using L-shaped tiles. What we've also done is we have developed an algorithm for tiling a floor with L-shaped tiles. So suppose, you know, I decide to open a business and I'm going to tile people's floors using these L-shaped tiles. And someone comes to me with a room, and that room is, you know, 16 by 16. And they want me to tile their floor with these L-shaped tiles. I can take their money and I can say, yeah, I can do that. Okay? And what am I going to do? I'm going to split the room into 4 pieces so that each of these is an 8 by 8. And I'm going to go to my friend who also has a similar business but only does 8 by 8 rooms. Right? I do 16 by 16 rooms. My friend does 8 by 8. And let's say that, you know, there's a missing tile right here. Right? So I'm going to go to my friend and I'm going to hand them, you know, this section of floor and say, hey, can you cover this 8 by 8 room for me? And they'll give me an arrangement of tiles that does that. And then I'm going to, you know, pop out the corners here. And I'm going to go back to my friend 3 more times and say, hey, can you cover, you know, this 8 by 8 room with a missing corner? Yeah. And I'll get them to cover this, and I'll get them to cover this. And then I'll take their solutions to those 4 8 by 8 rooms, and I'll use that as a guide to tile my 16 by 16 room. Now my friend who specializes in 8 by 8 rooms, what do? They take the 8 by 8 room that I've just asked them to tile and they break it into a set of 4 by 4 rooms. And, you know, there'll be one tile missing from somewhere in that. And they've got a friend who specializes in 4 by 4 rooms. And they'll go to that friend and say, hey, here's a 4 by 4 room with a missing tile. Can you cover that for me? And they'll say sure, and they'll come back with a solution. And then they'll pop out a corner from each of these and go to their friend 3 more times and get each of these rooms tiled. They'll take those, put them together, get a solution for the 8 by 8 room, hand that to me, I'll put that together to get the 16 by 16. And how does our friend who does 4 by 4 rooms do their job? Well, they're going to break their 4 by 4 room into pieces that are 2 by 2. And let's say there's a missing tile right here. So they'll go to the 2x2 friend and say, hey, can you cover this room for me? I guess this missing tile would be pretty big at this point. They'll say, hey, can you cover this room for me? And their friend will give them a solution. And then they'll pop out, you know, a corner here and say, how about this 2x2? Yep. How about this one? How about this one? They'll get solutions to each of those, put them together. That's their 4x4 solution, which they hand back to my friend who put those together to make an 8x8 solution, which they hand back to me, which I use to solve the 16x16. So it keeps going, but it's got to end at some point. You can't just keep hiring friends to do your work. Eventually somebody has to do the actual job. Well, this person, you know, goes to the 2x2 store. And the person there, they specialize in tiling 2x2 rooms with one missing spot. And they say, hey, can you tile this? And they're like, yeah, come back in 2 weeks, I'll have a solution for you. And they go to their magic key and say, oh, let's see this. Oh yeah, I'll put the L-shaped piece down there. And they put an L-shaped piece down there and hand that back, and they say, here you go. And that person uses that and goes back 3 more times, puts that together to get the 4x4 solution, hands that to my friend who visits 3 more times to get the 8x8 solution, and after doing that 3 more times, I take those 4 solutions and get my 16x16. So almost nobody did any real work. Mostly, each person just went to a friend, got them to do the hard work, put their solutions together. I didn't have to think to do this. I just had to find someone who could solve these 4 8x8 questions, and then I just, you know, copied them onto my guide, and then I just went down and laid down the tiles. The only person who did any work was the person who runs the 2x2 store, and you know what? They didn't actually do any work either. They just looked up their answer. So nobody's doing any work, but guess what? We just came up with a solution for tiling a 16x16 floor. And what happens if you don't have that friend? Well, here's the real trick. There is no friend. That friend is you. So you have a hat which says, you know, 16x16 person. And it's like, oh, I need to find someone to solve these 8x8 problems. Well, you take off that hat and you put on the hat that says 8x8 person. And that's your job, and you just solve these 8x8 questions. And how do you do that? Well, you break it into some 4x4s and you put on your 4x4 hat and do that. Alright, feeling a little weird at this point? Yes, it's true. It's not a problem if the missing tile happens to be, you know, in the middle anyway. It's missing from one of these quadrants, and that quadrant, you know, is a 2 to the n by 2 to the n with a missing tile. And these other quadrants are complete, so we take out a tile from each corner. Now each of these 4 quadrants is a 2 to the n squared with one missing tile. Alright, so this is going to be a recurring theme, right? We can use an inductive proof to show something, but sometimes in the construction of that proof we will actually end up with an algorithm for solving a problem. And there's 2 things I want you to keep in mind about this particular example of that. One, right, the algorithm we came up with for solving the problem involved solving smaller versions of the problem. Right? That's the essence of, you know, when we're doing the inductive step showing Pn gets you to Pn plus 1, while we're trying to solve this problem for n plus 1, we break it into the solution of problems for n. The other thing to observe is, you know, the comment someone made, this has to end somewhere. For us, it ended when you needed to tile a 2x2 floor. That's the base case. Now, if there was never a base case, this would go on forever and ever. I don't know what would happen when you had rooms that were like, you know, an eighth by an eighth or something. But the base case is where this process ends. It's where the buck stops. And you say, I'm going to actually give you a tiling solution, and I'm going to figure it out. I'm not going to go to anybody else to get the answer. That's what the base case is. P of 1 is true not because P of 0 was true. P of 1 is true for some other reason. And that's the starting point. And as we develop recursive algorithms in 222, we're going to see the same pair of elements in all of our code. We're going to see an element that looks an awful lot like this, and we're always going to see a base case. And when we forget the base case, we're going to segfault. All right, so we're going to keep going through this. This is like immersion therapy. We're just going to keep going deeper and deeper into this, and then at some point you may have crazy dreams about sunflowers that contain sunflowers, or Whoville or something like that, and that's where your brain will rewire itself. Let's go on to another example. Look at postage stamps. So let's say you want to mail a package to somebody, and you have to put a certain amount of postage on it. And you have an infinite supply of 3-cent and 5-cent stamps. Yeah, very Inception-esque. Infinite supply of 3-cent and 5-cent stamps. And let's just say, for the sake of argument, your postage is going to be bigger than or equal to 10 cents. And we would like to know whatever the postage is, 17 cents, 295 cents, whatever it is, can we always use our 3-cent and 5-cent stamps to make exact postage? Or is there some combination? Like, there's no way to get 7 cents out of just these. But we can get 8 cents, that's a 3 and a 5. We can get 9 cents, that's 3 9s. We can get 10, that's 2 5s. We can get 11, that's a 5 and 2 3s. We can get 12, that's 4 3s. So from 10 cents on up, can we always make exact postage? And the answer is yes, and we can prove that with mathematical induction. So let P of n be the proposition you can get n cents out of some combination of 3-cent and 5-cent stamps. Now this we can make mathematically precise pretty easily, but then it gets really muddled, because you're talking about, you know, integer equations and linear algebra and stuff like that. So I'm going to keep this one pretty informal too. P of n will be the proposition that we can make n cents postage out of some combination of 3-cent and 5-cent stamps. There is a pattern. We're going to pretend that we don't know that, though. All right, so we want to prove P of n for all n bigger than or equal to 10. So we're not starting from 1 as usual, we're starting from 10. But we're still going to use mathematical induction. So step 1, we need a base case. Let's prove P of 10. Well, P of 10 is pretty easy to solve, right? How do we get 10 cents postage out of 3s and 5s? Just use 2 5s. In fact, no particular amount of postage is that hard to do. But we want to show that, you know, this is true for 18,295,617,512 cents. And we don't want to actually work that out, right? So we finish this proof and we'll know that's true. Okay, so first part is the base case, and that's easy to show. Step 2, we need the inductive step. We need to prove that if we can make n cents postage, we can make n plus 1 cents. If we can show this, where n is bigger than or equal to 10, we're done. Mathematical induction. And it turns out it's pretty easy to show this. And just like before, there's going to be a series of cases we have to deal with. In particular, two cases. Case 1. If the solution for P of n includes a 5-cent stamp, replace it with a pair of 3-cent stamps. So we're given P of n is true, which means we can make n cents postage. Okay, so there's two possibilities. If the solution for n cents includes a 5-cent stamp, I'm going to take that same solution, I'm going to get rid of the 5-cent, I'm going to put in two 3-cent stamps. What happens to my total postage? If I get rid of 5 and I put in two 3s, it goes up by 1. Right? The solution for n means some combination of stamps that adds up to n. If I take away 5 and I add 6, I've now got n plus 1. So that would be a solution which proves P of n plus 1 is true in that case. But there's another case. If the solution for P of n does not include 5 cents, then we can't get rid of a 5 and replace it with a pair of 3s. Okay, if there's no 5-cent stamp though, then all the stamps must be 3 cents, right? And since n is bigger than or equal to 10, and our postage is made up of only 3-cent stamps, there have to be at least 3 3-cent stamps. So yes, remove 3 3s. And replace with 2 5s. If there's no 5-cent stamps, we only have 3-cent stamps. N is bigger than 9, so there's at least 3 of those 3-centers. Take away those 3 and replace it with 2 5s. Our postage has gone up by 1. And those are the only two possibilities. Either the solution for n has a 5-cent or doesn't have a 5-cent. And in either case, we've shown there's a solution for n plus 1. So P of n plus 1 is true, which means this inductive step is true. Combined with the base case and mathematical induction, we've shown P of n is true for all n bigger than or equal to 10. So yeah, you can always make this postage. So that's a nice inductive proof, but again, it's also an algorithm. So suppose we want to write 17 cents as a sum of 3s and 5s. Well, all we need to do is look at the solution for n equals 16 and do one of these two steps. Well, how do we find the solution for n equals 16? Let's look at the solution for n equals 15. Well, to do that, we need the solution for n equals 14. To find that, we need the solution for 13. To do that, we need the solution for 12. To do that, we need the solution for 11. To do the solution for n equals 11, we need to look at the solution for n equals 10. But guess what? We have a solution for n equals 10. It's right there in the beginning of our proof. Do a pair of 5s. So let's write 10 as 5 plus 5. Okay, well, if our only goal today is to prove P of 11, right, what does this do? Well, break yourself into two cases. Look at the solution for n. If it has a 5-cent stamp, replace it with a pair of 3s. Okay. Solution for n had 2 5s. So I'll take that 5 and replace it with a pair of 3s. Okay, let's pop back one level. Let's solve for n equals 12. If the solution for 11 has a 5-cent, replace it with a pair of 3s. Well, the solution for 11 does have a 5-cent, so I'll replace that with a pair of 3s. What about the solution for 13? Well, look at the solution for 12. If it has a 5-cent, replace it with a pair of 3s. Oh, solution for 12 doesn't have a 5-cent. Well, it says in that case we should have at least 3 3s. So let's remove 3 of those and replace it with 2 5s. Okay, I'll get rid of those 3 3s and replace it with a pair of 5s. I'm not going to keep flipping the page at this point, but to solve 14, look at 13. If it has a 5, replace it with 2 3s. To solve 15, look at the 14. If you have a 5, replace it with 2 3s. To solve 16, look at 15. If it has a 5, replace it with 2 3s. We don't have a 5, so take a pair of 3s and replace it. Take 3 3s and replace it with a pair of 5s. And then to solve our original problem, 17, the solution was find a solution for 16, replace a 5 with a pair of 3s. Well, there's the solution for 16. Let me take that 5, replace it with a pair of 3s. And there's a solution for 17. Now that felt like a lot of work, but imagine that I had a friend who could solve any postage problem up through 16. All I would have had to do was this. Say, hey, tell me the solution for 16, and they would say 5533. And I would do one thing. I would take a 5, replace it with 2 3s. I'm done. Really, really easy. The trick is, where do I find this friend who can solve postage problems up to 16? Well, I don't know, but wherever they are, they don't have a very hard job either. As long as they have a friend who can solve problems up to 15. Alright, you seeing some of the patterns here? I'm not going to ask if this makes sense, but are you seeing some of the patterns here? Between this and tiling floors. This is the essence of recursion. And it's this basic idea of taking a problem and solving it by solving a smaller version of the problem and then turning that solution into your solution. So how do we make 17 cents postage? Well, let's just solve a smaller problem. Let's just make 16 cents postage. And if I know that solution, now I can turn into a solution for 17 without too much work. How do I do that? Well, it's one of two steps, either that or that. So we could write this up as an algorithm that says, you know, to find the solution for n stamps, do one of the two following things. And guess how we would prove that that algorithm actually works in all cases? We'd use mathematical induction. Any questions you want to ask at this point? There are a lot more examples we could do. We could go back and do some mathematical examples, or we can continue in this direction and do some even further off the deep end examples. And I don't want to do either of those things at this point. I want to leave this where it is. We can talk questions for the next few minutes if you have any, but I want to leave this where it is and let you think about it, right? And I'm going to invite you to not try to force this into something familiar or something that you've seen, but to just kind of let it sit and be what it is. And this is, you know, in many cases, a very different direction to take things. And if it feels unfamiliar, that's cool, right? You're getting your money's worth. You're learning something new. And if it feels confusing, that's absolutely okay, because it is pretty confusing. We're going to spend, you know, weeks going over this and digging deeper into it. We're going to come back to more examples next week and you know, put more specifics on this. And we're going to start doing this kind of thing in 222 tomorrow or next week. So let me leave it there for now, and just promise you that we'll come back to this and put more specifics on and get more and more practice with this. Let's see, comment. You could probably write something with modulos and if-else statements without having to do recursion with this, right? You probably could, and generally anything you can solve recursively, you can probably solve non-recursively within reason. But there are crazy functions out there. If you want a rabbit hole, take a look at Ackermann's function. But don't go too far down that rabbit hole yet. But that's a recursive function that I don't think we can define non-recursively. But these are, you know, examples that can be done recursively. But yeah, we could also come up with ways to do these. You know, if your sum is divisible by 5, just make a bunch of 3s. If it's 1 more than a multiple of 5, or it's 2 more than a multiple of 5, you can come up with cases like that. One of the goals in recursion is not having to think too hard, which sounds kind of strange, right? But, you know, as computer scientists, a lot of times we're inherently lazy, right? What's a computer? It's an amazing tool that will do your work for you. So a lot of what we do with recursion is we're trying not to be too clever. We're trying not to dig too deeply into a problem. And when we further develop trees in 222, we'll see some, you know, very intuitive ways to think about concepts, and trying to code these concepts would be incredibly complex. But we can actually code them at kind of this intuitive level using this kind of self-reference. And so recursive solutions are often ones that feel kind of lazy. And sometimes you'll look at your recursive code and it's like, how can this possibly work? Nothing ever happens in here, you know? And that's when you know that you're like deep in the recursive rabbit hole. Yeah, awesome, nice. It can be space inefficient. It can be time inefficient. But we'll have ways to analyze that and some degree of ways to deal with it. But yeah, in general, when you start doing less work as the human programmer, you're asking the computer to do more work. All right, so we'll call it good there. Friday, 12:30 midterm exam. Show up on time. Hop into Zoom. You can mute it, but stay in Zoom so that I can post clarifications and corrections and so on. 12:30 Friday. Be there on time if you can, and I'll give you the full 80 minutes to work on the exam. I'll be in office hours tomorrow morning at 8:45 if you have any lingering questions. Otherwise, have a good afternoon. Watch out for snow tonight, and I will see you next time.